She got her PhD from the University of Washington with Jiaoshang, doing, I believe, relativistic multi-reference stuff. And now she is doing a postdoc with Todd Martínez at Stanford, continuing to do multi-reference theory, more accelerated by machine learning and GPU and all the wonderful things Todd Martínez does. And she's going to tell us about her exciting electronic structure methods for non-adiabatics and accelerating discovery in general. And take it away. Thank you.
Thank you. Thank you for the introduction. And hello, everyone. I'm Lixin. So today I'm going to introduce about my exploration in accurate and efficient electronic structure methods for accelerating discovery. So basically, my PhD and postdoc path all centered around studying light-matter interaction. And usually, experimentally, we see this more in molecular spectroscopy. And then, as a theorist, we use our toolbox of electronic structure methods to decode the spectrum, and then trying to understand the nature at atomic and molecular scale, and then end up achieving a better control of this light-matter interaction. And in general, this is the very exciting excited state chemistry that I've been studying. So in this talk, I'm going to talk about my exploration so far. Method-wise, I will first introduce the relativistic electronic structure method that I was involved to develop, including X2C, MRPT2. I'll talk about it later. And then for my postdoc time, I was focusing on studying DFT correction for multi-reference methods. And then both of them will have, the multi-reference methods will have their real-world application in molecular spectroscopy. So first of all, I guess people are more interested in knowing light-matter interactions in heavy element chemistry. That this is a field that's not really often mentioned by theorists yet in the US. So basically, we are interested in it because it's important in terms of DNA damage and radiation therapy in hospitals. And for example, this gold nanoparticle, it's actually a very good carrier for drug inside human bodies. And then other area that's very popular this few years is the quantum information technologies by applying heavy element atoms to design qubits. So this is a figure combining spectroscopy theory in the DOE IQM EFRC project. So it's becoming more and more important but to study the excited state chemistry in heavy element chemistry, but also another aspect of the radiation matter interaction that's being important is the nuclear power plants and waste containment. So actually just in Washington State, in Hanford site, there has actually 586 square miles that's full of this storing this nuclear waste that's left from the 1950s because they've done that for the DOE weapons program. So it's been a long time effort for people in PNNL, Pacific Northwest National Lab, and also universities around the country, trying to figure out better ways to design containers and how to handle these nuclear power materials. So this is actually the goal of iDream project that I will later talk about that I was involved. So basically first towards accurate description, I think you guys all know the famous or traditional single configuration approximation, which includes Hartree-Fock and density functional theory. The traditional way of doing this using these methods cannot describe the chemistry at geometries away from equilibrium, and they cannot describe the chemistry with open shell configuration as well as electronic excited states. So, but of course, nowadays there are a lot of brilliant researchers are working on extending their capabilities, including the Martínez-Gordon's group at Berkeley. So their ability be extended, but traditionally people then still will move on the multi-configuration wave function to describe the above chemistry. So instead of using one single Slater determinant, the multi-configuration wave function, it's a series of configuration expansion, including all the single excitations from the ground state geometry, ground state configuration, and then also all the doubles and all the way until n electron excitations. So by including all these configuration expansion, then it end up reaching a full CI, full configuration interaction results. So in order to understand how much we gain from that, so if you see this example of a distorted hydrogen molecule, only by stretching them to 2 angstrom bond length, you can see a Hartree-Fock energy, and the full CI energy can have 0.1 Hartree energy difference. So basically it's like 2.7 electron volt. And electronic structure theories define this difference called correlation. So this will be a very important concept that the whole electronic structure field is trying to recover as the correlation methods. The correlation energy. Yeah. So, but in order to recover the electron correlation, the first very important part of it is called static correlation, which mainly due to degenerate orbitals. For example, that means your wave function now have more than 2 configurations. That's both important to describe the phenomena. Therefore, the most famous one is the state average CAS-SCF method, complete active space, self-consistent field theory, to describe those systems. So basically the wave function, it's a full CI expansion inside this CAS active space. And then the core space, I also call inactive, will be just doublet fully occupied all the time, while the virtual will be no electron excited into. So this significantly reduce the cost of the configuration expansion, and then but also can qualitatively correctly capture the chemistry across different geometries. So this makes this method very popular. Based upon that, then the rest of the correlation, people usually define it as dynamical correlation. And one way on top of CAS-SCF to recover the dynamical correlation, it's by doing it variationally, doing a further configuration interaction on top of the CAS wave function. So that's the so-called multi-reference configuration interaction methods. While the other way will be a cheaper way to do it perturbatively, i.e. you can imagine MP2 method on top of Hartree-Fock. Here it's a multi-reference PT2 on top of the CAS-SCF wave function. So basically these 2 methods are the very expensive or sort of gold standard in a lot of chemistry applications. And besides introducing those methods, now we have this theoretical model chemistry. So usually we are talking about the 2 axes here, which is basic set. You have come all the way until complete basic set, and also a higher and higher level of methods. But now in relativistic chemistry, we also have another 3rd axis talking about what Hamiltonian we're using. So by including relativity, we can have 1 component, 2 component, all the way to 4 component Hamiltonians, where the 1 component here is usually non-relativistic Hamiltonian. So now, first of all, let's talk about what's the relativistic effect in like general feelings. So usually when we talk about relativistic effects, it will include scalar relativistic effects. That's more well-known. Like that's what it's determined why gold's color is gold, but silver's color is silver. That's because in silver molecular orbital diagram, its contraction, it's weaker compared to the gold element. Therefore, the scalar relativistic effect contracts the orbitals and make this excitation fall into the visible light range. And that's how we see the color as gold. So in practice, S orbitals and P orbitals will experience contraction, and D and F will experience expansion. And then a second large group of relativistic effect that's more, you guys might hear more, is the spin-orbit coupling, which means even for a hydrogen or deuterium atom, if you look at their fine structure splitting, you will see the 2p, the 3s excite down to 2p orbitals will have two spectral lines. That's due to the 2p orbitals can be split into 2p halves and 2p3 halves. So those are due to the spin-orbit coupling. So basically, many phenomena in heavy element chemistry can only be explained by including this relativistic correction, including chemical bonding and electronic spectra. So another example here is the extent of lanthanide 4f and actinide 5f orbitals in covalent bonding. So its molecular orbital diagram in coordinated compounds will look very complicated, and it definitely requires us to include multi-reference characteristic and relativistic effects to describe its spectrum. So when it comes to relativistic electronic structure, people first often use perturbative treatment to include the spin-orbit coupling and the scalar relativistic effect. Basically, we use a Hamiltonian that's just a non-relativistic with a scalar correction in it. And then we solve the electronic structure problems using this Hamiltonian. And afterwards, we add in the spin-orbit coupling part with the non-relativistic wave functions, and then construct perturbation. So then we add on the SOC part. So famously, for example, in MolPro and OpenMolCast, they have CAS-PT2 SO and MRCI SO methods. They were included via state interaction kind of manner. So, but importantly, here the spin-orbit coupling are not included in the MO level as I just described, because you solve the wave function in the non-relativistic Hamiltonian basis. And comparatively, another very important treatment will be variational treatment. In this way, people use actual relativistic Hamiltonians, which includes SOC correction at the molecular orbital levels. So we include all the relativistic effect at the beginning of the Hartree-Fock or DFT calculation, and then all the way until later the higher level electronic structure methods. For example, the 4-component one is almost the most accurate Hamiltonian right now in electronic structure theory. Of course, it's still approximated from the QED, the QED theory. So a lot of them can be found in a lot of relativistic books, but here I won't mention too much. So in general, the 4-component Dirac Hamiltonian still looks like the same kind of Hamiltonian that we always use, including a nuclear-nuclear interaction part and a 1-electron part and a 2-electron part. But the difference is the 1-electron part now look different, and the 2-electron integrals all look different. And these Hamiltonians will include not only just scalar relativity, and spin-orbit coupling, and also other tiny effects, including spin other orbits and spin-spin orbits. So those describes the electron spin and nuclear spin, or electron spin and electron spin interaction. So before our group, Toru Shiozaki actually have used this 4-component Dirac equation inside bagels. So he has already developed a 4-component internal contracted CAS-PT2 and 4-component internally contracted MRCI. And then Xiaosong and another senior grad students in the group at that time has implemented all the relativistic integrals inside our group software called Cronus Quantum. Therefore, that enables us to use these relativistic Hamiltonians in our higher level methods. So, however, 4 components problem is so expensive, as the name indicates. Now, usually you have one component, like one basis set. Now, because of the 4-component part, you will have 4 times more basis functions, etc., and everything become more expensive. And the cost, of course, is hard to imagine. And therefore, another famous approximation used here is called exact 2-component. exact two component basically is taking the 4 component 1 electron Hamiltonian and diagonalize it. So therefore you get exact transformation matrix to fold the 4 component Hamiltonian into the positive and negative part. And then this successfully reduced the computational cost. And then by using only half of the Hamiltonian, we can reproduce the positive energy spectrum of 4 components. And then we include the 2 electron SOC by using empirical Boltzmann factor, and the whole formalism is Cramer's unrestricted. And our group previously has already, Xiaosong's group previously has senior students and postdocs already implemented X2C, CAS-SCF, and X2C MRCI. So my work, actually, it's based upon that. I was developing the relativistic multi-reference perturbation theory on top of all those. So I was implementing the relativistic MRCI in Cronus first. And then I figured that if I rederive the MRPT2 equation, I can actually take advantage of the MRCI code to run a PT2 calculation and makes a lot of things way cheaper than the MRCI. So the whole idea here first, it's the partitioning schemes here. For MRPT2, you partition your Hamiltonians into an H0 and the perturbation V. And here I'm partitioning it so that my H0 only use a 1 particle fault time operator, which makes the calculation of all 0 order terms way cheaper. And then the second important partitioning scheme is partitioning the configuration space. So here the P will be the states of interest, and the Q will be the rest of the CAS determinants inside the CAS wave function. And the S, it's the external space, which the excitations from CAS the excitations outside of CAS are all included in this external space, which are the correlation relevant determinants that we want to include. So those are the main equations here, and the whole MRPT2 can actually reduce to MB2 if I'm using a Hartree-Fock single reference. And only all the determinants single, double excitations will be contributed to the first order wave function and the second order energy. So therefore, I can reuse the whole MRCI or say RAS kind of framework to design for the MRPT2 excitations. And then here are the how I rederive the equations to use the same framework as MRCI to compute the energies and first order wave functions. So we can skip here, and unless anyone is interested in looking into it more. So we also implemented a multi-state formalism to achieve a multiple excited state description. So basically, at the end, the relativistic MRPT2 for accurate description has involved the relativistic effect variationally in the Hamiltonian, and then dynamical correlation is recovered perturbatively. This method, it's about like 10 times way cheaper than MRCI and makes it possible to do a molecular potential energy surface here for a thallium hydride. So on the left,
you just have to generalize MRPT to X2C by including the second set of basis functions, right?
Yes. It's
the formalism doesn't look very different than MRPT, right?
No. The formalism doesn't look really different. The key difficulties here is all the now once you have relativistic Hamiltonians, everything like complex conjugate and stuff need to be carefully taken into account rather than assuming everything is real.
Right. Okay.
So that's the main difficulties.
All your electrons become imaginary, right? So,
yes.
Imaginary things. Yeah. Okay.
Yes. So here on the left, it's a thallium hydride dissociation curve including the ground state and first excited state without spin-orbit coupling. And you can see that it's just two clear curves. But then once you move to using relativistic Hamiltonian with spin-orbit coupling, the ground state still look like one because there's no splitting involved. However, the first excited states now split into 4 microstates, and only with the relativistic Hamiltonians you can get all these correct, which is very interesting in this case. So now I'll move on to talk about the iDream project that I mentioned earlier. So iDream, the full goal is to describe the interfacial dynamics in radioactive environment and materials. A whole key focus of the project is the chemistry driven far away from equilibrium. And we are very curious about the radiolysis across time scale and length scales. So it includes solution, interface, and bulk solid in the systems that we are interested in. And we also interested in ultra-fast dynamics and even longer timescales. And my role in this project will be study the spectroscopy in this ultra-fast timescale. And so far, in order to experimentally study this chemistry, we only have XFEL POMPRO techniques to use. So therefore, at that point, my collaborators actually did the experiment at SLAC. So here it's the SLAC light source, which goes through the whole Stanford campus, as well as the SLAC laboratory. So I think that's very close to you guys, and I'm not sure if you guys actually come and visit, but when I was a PhD student, I find it really cool. So then that actually drove me to like trying to get a postdoc experience here. So I went to a public tour straight away after I came here around SLAC. So that seems really cool. But then anyway, so then my collaborator, they came to SLAC and then did the first experiment in condensed phase that used all attosecond X-ray pump and X-ray probe, X-ray transient absorption spectroscopy. And they actually end up getting the spectra at a time interval of 600 femtosecond, sorry, 600 attosecond of 600 attosecond of the time. So it's really, really, really short. Basically, the idea of the experiment is first, the X-ray pump is going to pump out 1 valence electron from the water, liquid water. Once the valence electron is pumped out, then the X-ray probe is coming in to excite the oxygen 1s electron into either filling the hole or go to higher virtual orbitals. So then we get spectra. So we want to see how, once the valence electron is pumped out, how everything start to relax and collapse in the liquid water system. So this is the spectra that the experimental collaborator have gotten. So then they basically had observed these 2 block of peaks. That's interesting. So I would then later use theory tools to explain that. So as I just showed, because of the configuration, it's first you start with a whole configuration, and then later you actually observe way more holes in the configuration. Therefore, multi-reference method is really needed in this case because it's very open shell, and it's also a deeply hole, not just on valence orbitals. First thing of this research that we find out is that it actually solved a long-standing debate about liquid water X-ray emission spectra. So as is well known, the X-ray emission spectra of liquid water usually showcase a 1b2, 3a1, and also the 1b1 orbitals here has split into 2 peaks. That's been reproduced a lot, and people trying to study a lot about why. So there are 2 main hypotheses, is that, oh, maybe liquid water has 2 structural motifs existing normally. Or actually there is ultra-fast dissociation appearing in the measuring of X-ray emission spectra. Therefore, we can see 2 peaks. And since our experiment was done actually the same process, but in reverse compared to X-ray emission, because what we do is from 1s to fill the valence holes, while X-ray emission spectra is the electron from valence holes, from valence orbitals jump down to fill the 1s hole. And what we can achieve is we did 0.6 femtosecond, which is really fast, while the X-ray emission spectra can last way longer in the measurement. So again, come back to this spectra, we didn't see splitting in the 1B1 at all. Therefore, we can certainly determine that in the liquid water, these two peaks splitting is not due to two structural motifs. Because if there are two structures in the liquid water, our ultra-fast spectra can also see two peaks. So this is very interesting, and then leaves other theorists to continue to study the ultra-fast dissociation story. So again, any question?
No, it's just interesting. Yeah, I mean, have you considered doing the non-adiabatic dynamics, or is that under?
That's actually a good point, because when I joined Martínez group, they actually I don't know if you know Benicius. So he used to be a postdoc at Stanford in Martínez group, and they actually published a paper on they use like nuclear quantum effects of the hydrogen and then study the non-adiabatic dynamics. And they think it's ultra-fast dissociation causing the two peaks.
Cool.
So that was very interesting. It's when I joined, they actually like finished writing the draft. So then we had very good discussions on that.
Nice, nice.
Yeah. And then, yes. So the experimental spectra on the left side, it's the valence holes peaks, which corresponding to a configuration, as I said before, it's the 1s orbitals go up to fill the valence hole, which causing the 520 to 527 electron volt the peaks. So this is easy to solve also in the multi-reference methods. And then we also consider the possibility, because even though some of the water get their valence hole being ejected out, there's still some normal usual water in the system because it's liquid water, it's a bunch of water. So we consider another type of excitation, which will be just the 1s hole go to the valence. Sorry, go to the virtual orbitals, and the valence are all fully filled. And the other type will be the 1s hole now actually didn't fill the hole, but they go up to the virtuals because the energy is enough. So we consider these three types of excitations in our calculations, and we can actually reproduce the spectra compared to experiment because it's a different spectra. So I compute the before pump and after pump. So then we can get the different spectra correct. But still, we are very confused about why there's a bleach here. Like, what is the physical phenomena behind it? So now we were first thinking is the cationic water with a single hole itself the reason for pre-edge features. But clearly, we can just run a really quick simulations on H2O plus, which matches with experiment, and it's not the reason causing the bleach, because the peak actually just gets shifted a lot to the right-hand side. So it's nothing to do with the bleach. And then I then went back to, because I was doing a multi-reference configuration calculation here. I can get out each excitation configurations and then do a natural transition orbital analysis. And after doing this, we see that those bleach are actually caused by the fact that the excitation involved, it's actually on the center atom here, on the center water here. But because these water on the side has get excited, so it becomes an H2O plus. So with a cationic molecule on the side, these excitation actually get shifted. So this is a star shift of a neutral water pre-edge due to the presence of a spectator valence hole in a neighboring water molecule. So this is
explain what the bleach means. What does bleaching mean?
Oh, just like it actually just go down here.
Oh,
This,
compared to what?
Compared to like flat, usually you see peaks. But the absorption actually went down here.
So what's the explanation for that you found? It's that the.
So it's basically due to the fact that I'm calculating before and after pump here. And then due to this peak has shifted afterwards, after the pump. And then if you do the different spectra, and it shows a bleach.
Okay, gotcha, okay.
And
okay.
we're trying to find out why this peak gets shifted. So that's because in the excitation happening in here, like my mouse can show, but then if next to you there's a cation, a charge, that will cause a star shift.
Okay.
So I think that's I'm not sure how much familiar you guys are with Steve Boxer's work, like biophysics, electric field star shift stuff. So that's pretty relevant. Steve Boxer at Stanford, sorry. Anyway, so then now it moves to what I've been looking at during my postdoc, the first year at my postdoc. So I was curious about multi-reference methods are being so expensive in my past experience. So I was like, how is it possible to bridge the divide between CAS and DFT? Because the key to the simulation of all photochemical processes, especially if I need to model the dynamics of content-based system, I really need an efficient methods to reliably give out excited states, include the potential energy surface, including multiple excited states. So for example, if we want to study a GFP-like proteins or even an iron carbene photosensitizer, they all involve a multi-reference characteristic, and they need the dynamical correlation to be involved. And they, of course, needs a very, the methods to be very scalable. So what can we use to simulate when the standard CAS type methods are not suitably accurate and single reference methods are not applicable? And then the actual MRCI CAS PT2 are too computationally demanding. So now that's why I was like trying to figure out if we can add DFT corrections to help. And if we look back in the electron correlation concept, and if we did write the energy out as the kinetic energy and nuclear electron interaction, and then the Hartree part and the exchange part, and then the rest will be correlation, including correlation that's non-dynamical and correlation that's dynamical. So the first four energies sum up to be the Hartree fault energy, as we all know. And then this is a definition by Loudon, the difference between the exact non-relativistic energy, i.e. for CI, and the Hartree fault energy will be called correlation. And then normally, as I also just mentioned at the start, this non-dynamical correlation, it's the so-called static correlation, which we recover with CAS SCF, and the dynamical correlation will be recovered by CAS PT2 or MRCI. And this is indeed Handy's separation back in 1996, because he's more like a CAS person. So he was doing this separation from the perspective of wave function theory. However, after I study about this problem a lot, I think the actual question to ask is this the right separation? Because this is separation, it's actually really vague and it's really hard to like capture each of them. But still, we were building upon this and trying to further look at DFT now. So DFT can also be written in the similar form, but by replacing the correlation and exchange energies to EXC with the density rho. So the issue is the form of exact exchange correlation functionals is unknown. And this is a single slated determinant formalism. And of course, it has a lot of delocalization error, etc., that people can go to look more into the science paper published by Wei Taoyang in 2008 to understand more. But but you can't deny that DFT is super efficient in capturing dynamical correlation. So therefore, this is the question, and also many scientists have been trying to figure out, is it possible to achieve the best of the two worlds by combining the two methods? So for DFT, it's missing the non-dynamical correlation. And then for the CAS SCF or even the general valence bond SCF type, they miss the dynamical correlation. However, the dotted line here also means that in DFT, it is well known that some of the exchange correlation functionals actually involve some kind of static correlation. And in CAS SCF methods, especially in its CAS CI expansion, you definitely have some kind of dynamic correlation involved. That's inside the CAS space. Therefore, the main question people encounter in combining these two methods is the double counting issue. So far, all this kind of different multi-configuration DFT has, in the past 30 years, I would say, has now led to several mainstream of methods, including RAGs, which requires active space specific implementation and different particle-particle or whole time Dankoff approximation, or DFT/MRCI. Like, there are a lot of different ways. And then the multi-reference spin flip TDDFT or multi-configuration pair density functional theory. And also the still under active development is multi-configuration range separated methods. So I have provided several reference here for each of them. So if people are curious, they can look into it more. And I think I don't have the time to explain them one by one. But the difficulty here is mainly to do with describing excited states and describing cortical intercession. None of these methods are proved powerful enough to accurately describe all of this. So where I started in TerraCam, which is a GPU accelerated package, was work done 2017 in the past, where the authors, building on top of CAS CI, they simply replace the inactive part of the electron energy to DFT energy to introduce this DFT correction. So this is because of the CAS CI energy can be written as a general form of using 1 RDM and 2 RDM density matrix to compute the energy. And then you can write out, due to the active space separation, you can write it out as inactive energy plus active space energy. So you can see the whole formalism as active electron. It's embedded inside the pool of inactive electrons or core electrons here. So by replacing these inactive energies to a DFT computed inactive energy, because this formalism here is actually a Hartree-Fock-like in CAS CI. And then what he does is to replace this with EXC with the inactive electron densities in the AO basis. So in this way, there's no double counting. But of course, you're missing the active electron to virtuals dynamical correlation. And also this is not self-consistent. So it's rely on the orbital being really good from your CAS SCF straight away. So building upon this, I realized that in here, in the active space energy and the active electrons computation, the active electrons are still in a bath of Hartree-Fock inactive electrons because of this H core that's used. Therefore, what I did was to replace this H core, which is the Hartree-Fock-like formalism, replaced by a DFT-Fock-like operator. So therefore, you can understand the whole system as the core active electron was embedded inside the pool of DFT core electrons. So by doing this, again, the inactive electron density is the same for every excited state. And this inactive electron density is always forever closed shell single reference. And this formalism avoids double counting. So I myself find that using a closed shell single reference configuration with DFT, I'll find it more safe because I don't trust DFT with open shell configuration that much. Also, this formalism, it has the easy adaptability to many variants of CAS methods. For example, the dynamically weighted CAS SCF, because the active electrons are still described by the CAS formalism. And then, but also again, this formalism, we will aim to minimize the size of active space because those active electrons are not described by DFT. So we're missing dynamical correlation there. But we do believe that the actual multi-configuration nature does not need too many configurations to describe the static correlation. Yeah, at the end, this is a first order approximation on the DFT of using DFT fork. So this formalism was implemented in TerraCam and then can be used after either CAS-CI or CAS-SCF calculation. And it can also use all functionals in libxc library. So one thing I did was the classic example of ethylene torsion, where this ethylene, if it's around its equilibrium geometry, you can see the pi orbitals and the pi star orbitals and the 3s Rydberg orbitals. Those are the 3 orbitals involved in the CAS active space. For those first several excited states described here, the NV Rydberg 3s and the Z's excited states. And then once the ethylene is turned into 90 degrees of this side of the CH2 has turned, then this pi and pi star orbitals will become degenerate, which makes it hard to describe the full potential energy surface across this torsion. This torsion axis. So first, I was testing a series of BIDMaP functionals with different amount of exact exchange involved. So here is just basically ethylene's excited, the 4 excited states at the ground state geometry, and then you can see different amounts of exchange definitely can affect its excited state energies. And based upon this, I was choosing this BIDMaP 1.0, which is 100% exchange, because it matches pretty well with MRCI results here. So then from then on, I was choosing this functional to describe this ethylene torsion. And this benchmark, you can see, first of all, the CAS HF lib here looks really close to the MRCI SD benchmark, and it's all smooth. The curve, it's not, there's no any discontinuity, which is very important for dynamic simulation. And then look closely to the crossing point, which is what dynamic people will care more about. You will see the blue line here is the crossing point for CAS SCF, and the purple line is the crossing point for MRCI. And you can see by lacking dynamical correlation, their crossing point will differ quite a lot in terms of the torsional angles. And then by including this DFT correction, we can actually move this crossing point way closer to the MRCI crossing points. And this is the same for the other crossing points here, is that you can see the CAS and the MRCIs differ quite a lot, while the DFT correction actually can help move it closer to the MRCI results. And then if we plot out the actual whole potential energy surface and look at the crossing points, you can all see the whole potential energy surface by using the CAS with the DFT correction. They're all continuous and there's no discontinuity inside the surface that will actually stop you running dynamic calculation. So in short here, we can see the CAS SCF with one-step DFT embedding correction leads to a much more accurate topology of the potential energy curves of both. I didn't show the sodium chloride here, but I mainly show the ethylene scan compared to CAS SCF. And the methods here will be a promising alternative with high computational efficiency compared to MRCI and MRPT2 if we run dynamics. So, so far in here, I have talked about the three main stories of what I've been working on in the past, including relativistic second-order multi-reference perturbation theory and MRCI used for the all-attosecond X-ray pump probe spectrum for liquid water, and also the postdoc efforts of improving CAS-SCF with the DFT correction. So my postdoc work actually also involved using machine learning in our group's ab initio nanoreactor, trying to speed up the reaction discovery. And also some other projects involved using quantum descriptors for predicting photostabilities, because we find that if we include quantum mechanical data inside our training set, that can actually help the machine learning model to find a better answer. And then the DFT study I was doing actually builds the foundation of understanding what this dynamical correlation is missing in the CAS and can be recovered by DFT. And hopefully in the future, we can use machine learning to accelerate the multi-reference methods by combining the multi-reference and DFT. So here I have to acknowledge, I have to thank Professor Xiaosong Li's group and Professor Todd Martínez's group, and also thank you, Daniel, for inviting, and thanks you all for your attention. Thank you so much.
Yes, thanks, Daniel. Thanks for the wonderful talk. It's really interesting work. I just had a question. How do you decide, like, do we need to keep getting more accurate? Like, how do you decide when is good enough? Like, for the example of ethylene, like in dihedrals and those things, right? Like, when is it good enough?
So ethylene, it's a very classic photochemical systems that you basically need up to CAS-PT2 or MRCI in order to get the excitation energy correct compared to its UV-Vis spectroscopy. So this is a well-known hard system. That's why you need very, very accurate. But of course, for other systems, you can. So I mentioned at the beginning, you have a toolbox of electronic structure methods. You basically start from, of course, the best one, TDDFT, and then even higher level later, couple cluster or CAS methods. You basically look through them, and if any cheaper method can get you close to the experimental results, I'll say that's the good one. So
There's no machine learning yet, right? It's still quite slow, like these calculations.
Oh, so you think these calculations are still quite slow? Is that what you're saying?
Yes.
Well, with respect to DFT, but the thing is, like, she's interested in dynamics, so it's a much harder problem than just describing the.
No. I totally get the because one interesting thing we've been trying is we were adding MLIP, the one from Meta, into ab initio nanoreactor, and we are actually studying if we use MLIP and compared to we actually use ab initio methods, what gets it more correct, like what reactions can discover more and stuff like that. But I do agree MLIP is fast. But the design of MLIP here, even from Meta, they are just using the DFT omega B97MV functionals, rather than there are any multi-reference data involved. So you still don't know how good it can be for multi-reference system.
Dynamics was so hard.
Yes.
Yes. I have another question. So I come from more of like a traditional DFT background, and
Yeah.
Standing at the talk as you were framing the problems that you work on, you talked about handling spin-spin interactions, and I was clear about how you did that with like 4 electrons versus more like valence electrons. I'm thinking of like a pseudo potential and a basis set that doesn't explicitly handle 4 electrons. I was just wondering if you could go, I might be really having like a fundamental misunderstanding, but go a little bit back over that like background again?
Yeah, the relativistic part you're saying. Is that what you're asking about here? Yeah, so basically here the Hamiltonian is all electron Hamiltonian, so including both core electron and valence electrons. But you are very correct because people tend to recover relativistic effects by using effective core potential as well. And in that case, they were mainly considering the scalar relativity and even some amount of spin-orbit coupling, but not too much. Not too much of effective core potential have spin-orbit coupling so far, I think. But yes, those ones did not describe the core electron specifically.
Is that estimation, does that end up like really leading to like challenges with like accuracy?
Sorry, say again. I missed.
I was just wondering like how much that kind of,
Like effective core potential?
yeah.
You just don't have the core electron.
No, but I was just wondering how much that like actually affects.
Yeah,
like,
well, like she's doing like the X-ray stuff, right? So then you have to actually
Mhm.
describe the core electrons instead of just
so
pretending they
it's
don't
not
exist.
it's not an estimation that she would ever be using as an effective.
Well, not for X-ray spectrums. I mean, because ECPs, you're just literally deleting the electron
Yeah,
from your
exactly.
system.
And that's why I was so confused because I'm like, how can you handle since they're not
Right.
Yeah. So that's why.
Right. Yeah. Thank you so much for explaining for me, Daniel. Yeah.
I had a question on the DFT because I'm obviously a big MCP DFT fan.
Yes.
But so for describing you're integrating over the inactive density with your functional?
Yes.
Oh yeah, so like if your active space spatially overlaps with the inactive orbitals,
Mm-hmm.
don't you have to account for the active space density when integrating your functional, right? Because I mean, like
Yes,
it's not linear, right? Like if your functional is not linear, then it doesn't nicely separate.
Yes. That's why here I was saying it's only a first order approximation where, yes, I was assuming the exchange correlation energy hopefully can be linear, that I can just use the FOC, like the VXC here to replace it. But of course, as you say, that's a quite difficult problem. And one scenario we're thinking to use this method will be, for example, a molecule in in solutions. So you will have a bunch of solutions around which can be described by DFT, and the actual important solute can be described by CAS method. So in that case, that hopefully can be well separated.
Yeah, I mean, I think it would work fine for if you're like doing basically full CI on your molecule and then you have solvent, but right. But if you have to like separate out like an iron or something, it's probably yeah.
Yeah.
But yeah, you should check out the linearized pair density functional theory.
Yes, I saw. No, I actually see that and I used it already in PySCF. And I run it on ethylene. I ran the same, ran on the same torsion, the scan, and then I can see that it messed up something.
Yeah, that makes sense.
Yeah, I did benchmark it. The hard thing is the degeneracy part and the excited state potential energy curves.
Have you published the results on ethylene yet, or is this?
No, not yet. I'm still working on it. Like I'm not. So as you say, so here the first order approximation plus the fact that I miss some of the active electron correlation makes me really want to do better. I've been exploring how to do better than this, but I think this is just a hard problem, and that's why I'm hoping machine learning can end up helping.
Yeah, I mean, I think when I talked to Todd briefly, I mean, ethylene is like his white whale, right? It's like the
yes.
It's like the worst system, but so yeah, it's just hard. But okay, I'll look forward to the results. Yeah.
Yeah, thank you.